All right, so let's look at the Lagrange, not to be confused with Lagrange, Lagrange method of polynomial interpolation. Okay, what's good about this is we'll get a formula. Formula without calculation. Now, the problem is the formula is not a really nice formula to use. It's very cumbersome to evaluate. But nonetheless, we can get a formula without doing any calculation. So let's start with 2 points. So an x1, y1, x2, y2. And we want to find that straight line between them. Well, the basic method is simply that we're going to create y equals, and we're going to, for each point, we're going to make a very nifty fraction such that the fraction evaluates to the correct point here. So for instance, suppose I want this one, this first one, to evaluate to y1 when we put in x1 here. So we want y of x1 to be y1, but here if we make that y1, then this one will have to be 0, and this one we'll try to get to evaluate to be, say, y of x2 equals y2. And we could do this either way. I could make the first one y2 or the second one y2. But hopefully you'll see the basic pattern that goes with this. And the other one will be 0 when we do this. Okay, so how do we go about that? Well, okay, if I want this to evaluate to y1, I'm going to put a y1 there. And then what we want to do is when this is x1, we want this to evaluate to y1. So what I'm going to put here is x minus x2, actually. Okay, and I could do x2 minus x, but we'll kind of see what's going on here. Now, here's the thing. If x is x1, I get x1 minus x2 times y1. That's not what I want, but if I divide by that, x1 minus x2, then notice if I place x1 into here, if I put x1 into this thing, I get y1. But if I put x2 into it, y of x2 here, I get 0. So similarly, I'm going to do the same kind of thing here. Here's y2. I'm going to take x minus x1. Okay, so notice what I did. I took x minus the thing I'm not trying to get. So, I'm using the subscript 1 here. I used 2 there. And then here, same idea is when I put x2 in, I want to get 1, and so that's what I'll do. But if I were to put x1 into this particular side, I would get 0. So now I have this function that evaluates to y1 right here when I put in x1, and it evaluates to y2 when I put in x2. Okay, but what makes me think that's the right answer? Well, look at it. If you evaluate this stuff, you get a y1 over x1 minus x2 times x plus a y2 over x2 minus x1 times x, and then minus y1 x2 over x1 minus x2, and minus y2 times x1 over x2 minus x1. Well, so if I call that whole thing b, and I just pull out the x here and put this and this together and call them m, you see I get a y equal mx plus b. It is a straight line. So this is a straight line, and well, we know that a straight line through these 2 points is unique, and so that's the right straight line, and so that's the idea. Now, if we go to 3 points, okay, so go to 3 points, we'll have an x1, y1, an x2, y2, and an x3, y3. Now it's the same idea. I'm gonna have y, or I could call this my polynomial p of x. And so I'm going to start with a y1 times some sort of fraction plus a y2 times some sort of fraction. We'll put it down here, plus a y3 times some sort of fraction. And kind of going that same way, remember that what we had in here was like x minus x2. Well, we do that, but then we do x minus x3. So we just take all the points that are not subscripted 1. Here we take the points that are not subscripted 2. So x1, x minus x3. And here the ones that are not subscripted as 3. So x minus x1, x minus x2. And then in the denominator, we just use our x1 so that if we have x1 in here, we get 1. And so we do x1 minus x2 and x1 minus x3. X2 minus x1, x2 minus x3, x3 minus x1, x3 minus x2. And so notice each of these is a quadratic. Okay, they're each, I'm going to get, y times x squared divided by something, or yi divided by something. They're quadratic, and so I'm going to add, a lot of noise out there. I'll pause. So again, these are each a quadratic. And so when you add 3 quadratics together, you get a quadratic. And so we would get a quadratic polynomial through those 3 points. And real quick, with 4 points, I would have my p of x, and I would have a y1, and I would have x minus x2, x minus x3, x minus x4, so this is a cubic, divided by x1 minus x2, x1 minus x3, x1 minus x4, plus y2, x minus x1, because that's not a 2, x minus x3, not a 2, x minus x4, not a 2, divided by x2 minus x1, x2 minus x3, x2 minus x4, plus y3, x minus x1, because that's not a 3, x minus x2, that's not a 3, x minus x4, not a 3, x 3 minus x1, x3 minus x2, x3 minus x4, and then finally plus our y4, y4, x minus x1, x minus x2, x minus x3, divided by x4 minus x1, x4 minus x2, and x4 minus x3. So there we go. There is a cubic polynomial going through 4 points. And so in general, you see that's going to be the pattern. If I have n points, I can find a polynomial of degree n minus 1 or less that passes through the points. Okay, so that's the intuition as to why that would work, is looking at that Lagrange model. Okay, so we'll call that one done.